Vanakkam. Welcome to this video on biomechanics. We have been looking at kinematics. Specifically, in the previous video, we looked at forward kinematics of a two-link serial kinematic chain. In this video, we will be looking at 2R inverse kinematics, or in other words, if I tell you the endpoint coordinates of a two-link serial kinematic chain and the link lengths, can you tell me what is the joint angle at each of the links? This is the question, broad big question. It is a two-link chain, planar chain, no complications, not 3-link, not n-link, there are exactly 2 links. There are 2 links and I am telling you the link lengths and I am telling you the end point coordinate. What is asked? Can you compute the individual joint angles that each of this link makes with the ground? This is the question. Okay. So, what we know from forward kinematics is suppose I have I have these 2 links with lengths L1 and L2. Okay. If I were to express the coordinates of the end points, we did that in the previous case as x is L1 cos theta 1 plus L2 cos theta 1 plus theta 2 and y is L1 sin theta 1 plus L2 sin of theta 1 plus theta 2. This is what we saw. For convenience, I am going to call C1 as cos theta 1, C12 as cos of theta 1 plus theta 2, S1 as sin theta 1, S12 as sin of theta 1 plus theta 2. Okay. So, that means I am going to call this as L1 C1 plus L2 C12 and y is L1 S1 plus L2 S12. Okay. Now, so the equations that I have are, let us write this out again, x is equal to, let me erase this for convenience, I am going to erase this, I have already written this down. So, I am going to erase this. X is equal to L1 C1 plus L2 C12 and y is equal to L1 S1 plus L2 S12. Okay. Now, what I am doing, I am going to rearrange this equation slightly. Okay. I am going to write it such that the C1 and S1 comes to the left hand side, that is x is equal to x minus L1 C1 is equal to L2 C12 and y minus L1 S1 this is L2 S12. Now, I want to square these 2 equations. You are immediately wondering what is this person doing, why is he doing all these things? Because I am interested in getting rid of many complications. There are theta 1 plus theta 2. So, I am trying to have thetas, theta 1 and theta 2 in my equations, or first I find theta 1 which I will then substitute in the theta 1 plus theta 2 equation to find theta 2, because I am interested in finding theta 1 and theta 2 from L1, L2, x, y. Okay. So, that is the problem. So, I am having this in my head and I am working towards that. This is why I am doing some manipulation, some arrangements consistent with normal laws of algebra. So, no cheating, I am just doing whatever algebraic manipulations that are valid. So, I am having this as x minus L1 C1 is L2 C12 and y minus L1 S1 is L2 S12. I am squaring this on both sides. So, this will give me x minus L1 C1 the whole squared is L2 C12 the whole squared, is it not? Likewise, y minus L1 S1 the whole squared is L2 S12 the whole squared. I am adding these two. Why? Because L2 C12 squared plus L2 S12 squared, right. So, this will give me L2 squared times C12 squared plus S12 squared. This is sin squared A plus cos squared A or sin squared x plus cos squared x, that is 1. Okay. So, I can use that as part of my analysis. Okay. So, I am adding these two equations. Okay. What will I get? I will get x minus L1 C1 the whole squared plus y minus L1 S1 the whole squared is L2 squared into C12 squared plus S12 squared. But C12 squared plus S12 squared is 1. So, I will get this to be 1, or rather this whole left hand side is equal to L2 squared. Okay. But not just that, I also have to expand the squares on the left hand side, which I will do step by step. Okay. So, I am having this is a minus b the whole squared, that would be actually a squared plus L1 squared C1 squared b squared minus 2 times a into b, is it not? Likewise, for the y coordinate y squared plus L1 squared S1 squared minus 2 times a b. Remember, in this case a is y, b is L1 S1. Okay. This whole thing is L2 squared and I am bringing the L2 squared to the left hand side, which will make it minus L2 squared is 0. This is the equation. Now, I have L1 squared S1 squared plus L1 squared C1 squared. I can bring the 2. So, that would be x squared minus 2 x1 sorry minus 2 x L1 C1 plus y squared minus 2 y L1 S1 minus L2 squared plus L1 squared into C1 squared plus S1 squared. This is the, do I have the same number of terms? Check 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, correct. This whole thing is 0. Now, C1 squared plus S1 squared is 1. Because of this, this whole thing will vanish to 1. So, I will have only L1 squared. Now, rearrange this slightly and multiply this whole equation by minus 1. Okay. Just for convenience, I have this as 2x L1 C1 plus 2y L1 S1 plus L2 squared minus x squared minus y squared here we have left out a y squared here. Okay. Minus y squared minus L1 squared is equal to 0. Now, I am going to call this coefficient as sum, say capital A, and this coefficient as sum capital B, and this whole constant as some capital C. So, this can be called as A C1 plus B S1 plus capital C is 0. This is the equation that I have in terms of theta 1, that I need to solve, because this is C1 and S1, right, that is cos of theta 1 and sin of theta 1 I have in terms of this. Now, let us proceed in the next slide. Now, let us rewrite that original equation, which is A C1 plus B S1 plus capital C is 0. Now, this is the equation that we had. Now, divide this entire equation by square root of capital A squared plus B squared. What happens? That will give me capital A divided by square root of capital A squared plus B squared times C1 plus capital B divided by square root of A squared plus B squared times S1 plus capital C divided by square root of capital A squared plus B squared. The whole thing is 0. Remember, in this equation I have this right triangle with sides A and B, capital A and capital B, with some side psi, right. So, this is the situation that I am describing, right. Now, immediately in this from this right triangle, A divided by square root of A squared B squared is cosine of psi, is it not? That is cos psi, or in our notation that is C psi C1 plus B divided by, B is the opposite side to the angle psi, B divided by the square root of A squared plus B squared is the sine of psi, right, not, that is S psi S1, and this whole thing is minus C divided by A squared plus B squared. Okay. C psi C1 plus S psi S1. This formula looks somewhat familiar, is it not? That is sin A sin B plus cos A cos B is cos of A minus B, is it not? So, that would give me cos of theta 1 minus psi is this value minus C divided by square root of A squared plus B squared. Okay. Now, psi itself is what? The opposite side by adjacent side, is it not? That is tan inverse of B by A. Okay. So, if I want theta 1, I will get it as tan inverse of B by A plus cos inverse of minus C divided by square root of A squared plus B squared. Okay. This is the value of the first angle theta 1. Now, I need to substitute this angle in the original forward kinematics equation, which is this equation, for example, and find out the value of theta 2, and you will get, I will leave that as an exercise for you, and you will get theta 2 as cos inverse of x minus L1 cos theta 1 divided by L2, the whole thing minus theta 1. This is the value of theta 2. This will give rise to a situation in which there are at least two configurations AB and BP that can come either as these solid lines or as this dashed lines. So, there are two distinct pairs of solutions or two sets of theta 1 and theta 2 from the inverse kinematics problem that we are showing here as the solid brown blue line and the dashed brown and blue lines. These two solutions are also called as the two branches of the inverse kinematics problem or two branches of the inverse kinematics solution. Commonly in robotics and biomechanics they are called as the elbow up solution and the elbow down solution. So, from this exercise what we have learned is that even in the simplest case of a two link planar kinematic chain, the inverse kinematics is relatively complicated, that even in the case where the two link lengths are given and the two coordinates are given, the xy coordinates are given and the link lengths L1 and L2 are given, the theta 1 and theta 2 are not unique, there are at least two sets. In the case of the two link chain there are two sets of solutions, means because why is this happening? Because of the non-linear nature of the kinematic chain or the way in which we describe this kinematic chain, because of the sines and cosines involved. Sine inverse and cosine inverse, right, can refer to two different angles. Because of this reason we have at least two solutions that will satisfy a given equation. This is for the simplest case. Now imagine I have a large number of degrees of freedom, many multi-link serial kinematic chain. Then finding the inverse kinematics is a relatively hard problem to crack. This is just an introduction to the topic, so you get an idea of the complexities involved in the biomechanical analysis of multi-link serial kinematic chains. So, with this we come to the end of this video. In this video we studied and analyzed the inverse kinematics of a two link planar kinematic chain. Thank you very much for your attention.